I'm going to show a quick video. This is a real scan job done by with a Faro scanner. And Faro is the leading brand in LiDAR scanner. And I was consulting with them about purchasing one of their scanner, but it's just super expensive. I think the cheapest version is around $80,000. But anyway, this is it's really good scan. This is a 3D model created directly from their scan. So there's no further processing, but they just process this model and run the scan pretty much at the same time. You can see all the shape of people. You can see this one does not only include the geometry, but also the RGB information, the color and texture. That's all put in that. So the geometry was from the LiDAR scanner, and the RGB information, the color is actually from the camera. And there's a internal mechanism and algorithm to synchronize both information together. All right, so now imagine if you have this model, you can do a whole lot of things. And definitely I'm going to show you in a minute that we can also import this model to Revit, and we can do a lot of area calculation, distance calculation inside Revit. Give me a second. Okay. Okay, so that's a LiDAR scanner. And of course, LiDAR scanner is very expensive, even though its performance is pretty good. So there's another method that is more popular for general contractors for some simple scan. It's called photogrammetry. And the method used by that, a lot of times with different name, it's called structure from motion. Photogrammetry is generating a 3D model from a whole bunch of pictures. And you can tell from this video that sometimes you even do not need to take pictures. You can just download the pictures from Instagram, from Facebook, and you can recreate the 3D structure. So let me show you this video. Let me make sure I'm sharing the sound as well. Okay.
Who says Rome wasn't built in a day? With the muscle of about 500 computers and 150,000 still images, Steve Seitz and his colleagues at the University of Washington's Seattle campus reconstructed many of Rome's famous landmarks in just 21 hours.
The idea behind Rome in a day is that we wanted to see how big of a city or model we can build from photos on the internet.
With support from the National Science Foundation, they're rebuilding Rome pixel by pixel instead of brick by brick. Calculations that once took months now take hours.
This is the largest 3D reconstruction that anyone has ever tried. It's completely organic. It works just from any image set. People upload the photos and they suddenly appear in our models.
It starts with a trip to the photo sharing site Flickr to search for images of the real thing. Once pictures are identified, the computer starts the process of making 3D objects from 2D stills.
If I'm a sculptor, there are 3 photographs of me. We find the 3 points in those 3 photographs which point to my nose. From that, we know that there are 3 points in these 3 images which correspond to a single point in the 3D world.
Computers map huge clusters of these points into 3D space, creating ghost-like images called point clouds. Those squares represent the positions of the source photos.
For buildings, I think we can get accuracy to within, a few centimeters. So we've measured this. And for individual objects that are photographed closer up, we could potentially do a lot better, like, millimeter level accuracy.
Finally, color and texture are added. And what you get is a virtual 3D tour, like this fly-through of Dubrovnik, Croatia.
What excites me is the ability to capture the real world, to be able to reconstruct the experience of being somewhere without actually being there.
Look for this next generation technology to show up in online mapping sites, video games, and a whole lot more. It's a virtual guarantee. For Science Nation, I'm Miles.
Actually, you guys are using photogrammetry or benefited from photogrammetry every time. Let me show you how. So this is a Google map. I assume everybody knows that. And if you go to satellite, okay, and if you go closer, you use the shift button and your mouse. What you see is actually 3D models of everything. And this is Valhall. I'm right here right now. This is the stadium, very accurate. Let me ask you guys a quick question. How Google created the 3D models here? Did they fly an airborne LiDAR and do the scan? Anybody?
No.
No, of course no. That's too expensive. Google were using the satellites. They used the satellites image from different angles from the Earth and created a 3D model from using photogrammetry. That's all what happened. And before that, Google has been having this sort of creating the 3D world, 3D digital world for a long time. Their original way of doing it was building the 3D models manually. So they had this company called SketchUp. So originally Google is the SketchUp, actually Google SketchUp. And later they figured out a more efficient way of building the 3D models automatically. And they had algorithms to improve the accuracy and precision. So they sold, the SketchUp to Timber. Now it's the Timber SketchUp. So that's the story. And I actually see a lot of interesting projects. Google had all the 3D models, but they don't share the 3D models. And so I saw a guy, actually on YouTube, you can do this. They just basically do this. They just take a lot of screenshots by rotating the model like this. So they basically reproduce the images and they send it to the photogrammetry software. And guess what? They recreated the exactly same 3D models as Google's. It's pretty much everywhere. I used to have fun with this, especially for the big cities. I don't know, for smaller cities. Oh yeah, so see, it's just becoming, and also see the trees, guys. It's not just the buildings, and it's doing pretty good even with the trees. And did you guys play Google Earth VR before? Have you ever played the Google Earth VR?
Yeah.
And I really hope we had this face-to-face meeting. Usually I do VR research, and usually I play this. I ask my students to play, Google Earth VR. But let me show you for those who have never used this before. It's amazing. It's really relaxing. It's actually based on photogrammetry created 3D models. Let's do it next time. Okay, so maybe in the spring when everything clears out, I really hope you guys can come to my live and try it yourself. All right, so that's photogrammetry. You know how it works, and it's also rocket science. You know, in 2015, we sent this vehicle to the Pluto, and we, for the first time, we built this high resolution 3D model for the surface of that. Of course, we couldn't use LiDAR because the vehicle was on this solar panel. The energy is not enough to support the LiDAR scanner. They used photogrammetry. So they just took a whole lot of high resolution pictures and send the picture back to the Earth, and we run the photogrammetry quickly, and we have the 3D model. So what is photogrammetry? How can we reconstruct 3D model from 2D image? You know, let's assume this is a real object that we want to scan, and there's a point Q1. And now I take 3 pictures from different angles, you know, P1, picture 2, and picture 3. And so the 3D object will be the 2D, you know, projection on my plan. But of course, I will have the same points, the projection point from this real world point. So it's like called the Q11, Q21, and QI1, you know, different pictures. And you notice that the shapes look different because I'm taking the pictures from different angle. So if mathematically I can capture how the shapes are distorted from this picture 1 to picture 2, I can somehow understand, you know, how I moved from this point to this point. And similarly, if I can somehow tell how this rotation and the distortion of the shape moving from this picture 2 to picture 3 inform me how I moved my camera from here, so I can recover this one. So once I have this recover of this one, and also once I have, you know, for example, this line and this line is different, so I can also recover, you know, the distance from, you know, recover these 2 lines, the angle of these 2 lines, then I can recover the distance from this particular point to this point, and distance from this particular point to this point. So let me explain the mathematical foundation of that. I used to, the first time I heard about this photogrammetry technology, and I asked it a question like, what is photogrammetry? Why this is working? And the speaker gave me a very simple answer showing that this is kind of like a human eyes, you know, have 2 eyeballs, so we can triangulate, you know, the depth information. So it was making sense to me, but soon I noticed a problem. It's not the key of photogrammetry, because for us, yes, if you punch in my face, and because, you know, I have 2 eyeballs, I can somehow triangulate the distance so I can avoid your fist. But the thing is, my brain knows the location of my 2 eyeballs, and also it knows the distance between the 2 eyeballs. So actually I have enough information to recover the distance from your fist to my face. That's correct. But how, you know, if you hold a camera and moving freely, how do we know how long you moved and how you rotate the camera? So the key of photogrammetry is not triangulating the XYZ information, but is how to recover the camera is moving, how camera is moving. And this is the most difficult part. Before this, you know, this method was invented, people had to do some manual calibration work. So that, for example, they have to get the distance of between 2 points in the real object, and how to they need to move their camera carefully so they can basically triangulate the XYZ. It's kind of like you have to measure accurately the distance between 2 eyeballs so I can recover this distance, right? So we have to follow that standard. It's not flexible at all. Until a genius from MIT, he was at that time a PhD student at MIT, and I was thinking about a mathematical method. He said, you know, the distortion of the shape in my pictures should contain information for me to recover how camera is moved. So why don't we have this, use this infrastructure-free method? Why don't I discover some kind of mathematical principle to recover that, so we do not need to follow the strict standard for this photogrammetry approach. So this is what he discovered. He discovered 2 important matrix. Let me skip this part. So basically, one thing is called a fundamental matrix, one thing called essential matrix. So what is a fundamental matrix? So this is the real world shape, like a triangle. This is the projection. And basically this one is the projection of that, so it's different, okay? So fundamental matrix describes how the real world object is projected to this projected project. And we know this is a matrix calculation, right? So in order to change the shape and rotate the shape, mathematically it's matrix calculation. So if we define the XYZ of each corner of the shape, we multiply a matrix, then we have a different shape, right? So if I have multiple pictures and we check the distortion, then we can recover this fundamental matrix. Okay, so we know this is the real world shape, this is how it looks like, so this is the projection. This one shows the projection. And also we can compare from picture 1 to picture 2, how that projection is also different, because we are taking pictures from different angles, that's also different. And of course, this is a matrix, I multiply some matrix, I get this matrix. And that matrix is called essential matrix. So essential matrix describe how the camera is moving from this point to this point. So based on the fundamental matrix and the essential matrix, I can recover the pose of my camera for giving camera point, and also how I moved my camera over time. So this is how it works. And this method, he named it as structure from motion. This is the soul of today's photogrammetry method. Structure from motion. It's kind of like I can recover the motion from my camera from the structural changes, and I use that. It's kind of like now I know the location of my eyeballs and the distance between my two eyeballs. So now mathematically I can recover the distance between my head and this web camera. And fortunately, this guy didn't patent it. He made it free. So that's why nowadays we have seen so many applications of photogrammetry, especially drones. You guys probably heard construction companies really like use drones. A lot of companies actually fly the drone on a weekly basis. They are building 3D models of their job site. So they actually can calculate it automatically, the earth moving logistics. They can plan the flooding preparation. That's all because this guy who invented the structure from motion made it free. So we have a totally whole market. So this is the workflow, the pipeline for photogrammetry. So number one is we have to identify features. Picture picture contains a lot of pixels. For 1K picture, that means 1 million pixels. So we can now analyze that many. So we want to identify some feature points. So for example, like the corner of this toy car. And then we want to do the corresponding, which means I have 2 pictures and I have somehow do some computer vision analysis. So I know this particular point on picture 1 is this particular point on picture 2. So I connect them. Okay, that's called corresponding. And then I recover the camera pose using structure from motion. So basically I see how this object is different, looks differently in picture 2, and I recover the essential matrix and the fundamental matrix. So I recover the pose of my camera, and based on that, I can recover the XYZ information for this particular point and that point. So I create a dense model. So that's and then I recover this sparse model. The sparse point cloud model only includes the XYZ information of the main feature points I collected, and I run the interpolation until I have this dense reconstruction model. And finally, I feed the surface, very similar to the thin process, using the smaller triangles to simulate the surface of the object. So this is how it looks like. We identify the feature points, we recover the pose and the changes of the camera. So I can basically triangulate XYZ. And then I use some interpolation to get more data, dummy data points. And finally, I use small triangles to fit the surface. So what can be the potential difficulties? Because of the principles that photogrammetry is using, it does have its own limitations. So first, you do need good features. I tried to do photogrammetry on this glass cup. I couldn't do it because this is totally transparent. From the mathematical or from the computer perspective, it doesn't make too many difference among these pixels. So it's losing a lot of feature points. It's impossible. And also different size, like if you are further away from the object, if you're close to the object, the size appearing in a picture will be different. So nowadays we have an algorithm called a Swift algorithm. So this is a computer approach that can somehow check the features and rescale different scales. So it knows even though this car looks smaller, this car looks bigger, but they refer to the same car. So it's not a problem anymore. Another problem is different color and texture. For example, I try to download the Emperor building pictures from Google Images. Some of them are toys, some are real pictures. I couldn't finish the photogrammetry because to computer, they are different things. The texture point, the picture, the pixel values, the RGBs are so different. They don't recognize them as the same object. So that's also a problem. Distortion, sometimes because of the angle or because the camera you are using, like fishbowl camera, the pictures can be totally distorted. So in that way, we also run this Swift algorithm to correct them. And finally, the correspondence problem, that's also a big problem to a lot of photogrammetry applications. So when I did this scan, like in 2013, that's 7 years ago, I took only about like 20 pictures, but it took me about 1 hour to finish the photogrammetry calculation. But nowadays it can be much easier. So let me show you the model that I created, the first photogrammetry model I created 7 years ago. You see, this is actually the points and based on RGB information. All right, so let's talk a little bit about your next assignment. So your next assignment is the scanning project, and you need to use photogrammetry. I'm going to show you how to use some free software, open source software like MeshLife to do that. I'm going to show you that in a moment. And also an alternative is to use Autodesk Recap to do it. So what you need to do is I actually have this tutorial. Let me open that here. So what you need to do is to take a whole lot of pictures, maybe 80 pictures, not more than 100 pictures, because if you're using Recap for free account, they do not allow you to upload more than 100 pictures. So take some pictures and let me see, here it is. And then send it to any application such as, Autodesk Recap or the Mushroom, and create a 3D model. So you have to coordinate with a team member because you cannot take pictures separately and create one model. You have to, select what you want to do. And so this is some rule of thumb. If you are take pictures of a building and try to do this photogrammetry modeling of a building, usually you have to do the scan at least at 3 levels. And the higher you are flying your drone, usually we use the drone to do this building scan, the bigger diagram diameter you should use. So this is the best practice to capture all the needed information. And if you're doing this interior scan, for example, in your dorm room or in your apartment, if you want to just create an interior finish of that, so you need to stand in the middle and take pictures of that by rotating. And once again, try to make sure you have at least 3 layers of scan. And for 2 pictures, like let's say if you are using your phone and scan it, take pictures from different angle, make sure 2 pictures should have at least a 50% overlap. So that can help the algorithm to find the matching feature points more easily. So this is actually the tutorial for the Mushroom, which I'm going to show in a moment. And before that, let me show you a project that my students and I have done like a long time ago. It's a photogrammetry project with a drone. So let me see where it is. Should be this one. When I was at the A&M, we flew a drone over Francis Hall, and we took a shot video for 5 minutes, and we get the screenshots from the video, and we reproduced the 3D model of Francis Hall, and I sent it to Rabbit to play with it. This is the recreated 3D model of that. As you can see, these are the pictures, the screenshots from the video. You see the triangles? That's the team model, right? Okay, guys, so I'm going to give you a demo on this. As you can see, I'm going to do 2 scans now. So one is using this LiDAR scanner, and one is using the pictures I took. I'm going to do them all together. So photogrammetry plus this LiDAR scanning. So give me about 10 minutes to prepare the scanner. So let's meet again at 5:50. Okay, 5:53. See you guys then.